Another set of statements. With proofs. Statement: the sum of three consecutive odd integers is divisible by 3. Proof: let n be an element of the set of integers z. Then, 2n is an even integer. With this, let us have 2n plus 1, 2n plus 3, 2n plus 5 be the three consecutive odd integers. Taking the sum of the three consecutive odd integers, we have the equation 2n plus 1 plus 2n plus 3 plus 2n plus 5 equals 6n plus 9. This happened since like terms were combined like the three 2n's. Since 6 and 9 have a common factor 3, we can apply common monomial factoring, which gives us 3 times the quantity 2n plus 3. Obviously, 3 is a factor of the sum. This means that the sum is divisible by 3. Illustration: say the three consecutive odd integers are 3, 5, and 7. Their sum is 15. This 15 is divisible by 3. Statement: show that when n is any positive integer, the remainders are 1 and 0 if n is divisible by 4. Proof: since n is an element of the set of positive integers, then n can be even or odd. If n is even, then n is equal to 2k for some integer k. Hence, the square of 2k is 4 times the square of k, implying a remainder of 0. Now, when n is odd, we have n is equal to 2k plus 1, for some integer k. Thus, the square of 2k plus 1 is 4k square plus 4k plus 1. Now, the first two terms 4k squared and 4k are having 4 as a common factor. Hence, it becomes 4 times the quantity, k squared plus k, plus 1. This implies a remainder of 1. The sum of even and odd integers is odd. Proof: let m and n be even and odd integers, respectively. Then, there exist integers k and j such that m equals 2k and n equals 2j plus 1. Getting the sum of m and n, we have m plus n equals 2k plus 2j plus 1. Since 2k and 2j have a common factor of 2, we have 2 times the quantity k plus j plus 1. Hence, whenever we add an even integer and an odd integer, the sum would be odd. Another proof: by contradiction, suppose that m and n are the even and odd integers, respectively, and m plus n is not odd, that is even. There exist integers k and j such that m is equal to 2k and m plus n is equal to 2j. Now we have m plus n is equal to 2j. Solving for n in this equation, we get n equals 2k minus m. Since m is equal to 2k, we get 2j minus 2k. By monomial factoring, we have 2 times the difference of j minus k. We have shown here that n is even. This is a contradiction that n is odd. QED or end of the proof. The sum of any two odd integers is even. Proof: let m and n be the odd integers. Then, there exist integers k and j such that m is equal to 2k plus 1 and n is equal to 2j plus 1. Now getting the sum of m and n, we get m plus n is equal to 2k plus 1 plus 2j plus 1. Since 2k and 2j have a common factor, we could have 2 outside the quantity of the sum of k plus j. So result is 2 times the quantity k plus j plus. Since the expression has 2 a common factor of the terms, we have 2 times the quantity k plus j plus 1. Hence, the expression is even. Thus, for any two odd integers, the sum is even. Statement: the product of even and odd integers is even. Proof: let m and n be even and odd integers. Then, there exist integers k and j such that m is equal to 2k and n is equal to 2j plus 1. Now getting the product of m and n, we have m times n is equal to 2k times the quantity 2j plus 1 equals 4kj plus 2k. By common monomile factoring we get 2 times the quantity 2kj plus k. Hence, the product of even and odd integers is even. Thank you for watching. Please share this to the learners.